right, so hello everyone. Today is June 22nd. We are coming to the end of our 5th week. Tomorrow will be the last day, so we're moving right ahead. I will post the final exam on, I believe, on Saturday. So I need to make the final exam. It will be comprehensive, so the final exam will encompass everything. So we are going to go on with chapter 9. I just want to check where I left off. Just give me a brief second. All right, so I'm going to go ahead and share my screen. So yesterday we left off with this hydration. We talked about the keto-enol tautomerization. Remember, a tautomer is a constitutional isomer. So they have everything the same. The only thing different here will be where the proton is located at, and we discussed that yesterday. Anyone have any questions on this? All right, so we're going to hydroboration. Oxidation of alkynes is the same as for alkenes. We have regional selectivity for anti-Markovnikov addition. It also produces an enol that tautomerizes to an aldehyde. So we get the alcohol and the aldehyde in this case. First, we have a proton transfer. Then in the enolate state, this pair of electrons form a double bond here. Then we form this carb anion. A carb anion can then, the enolate is protonated by a water group in this case. This carb anion is going to take that proton from that water, and then here we see we have the aldehyde. So an enol is deprotonated to form an enolate, which is protonated at the carbon to produce the aldehyde. If borane is used, then the alkyne can undergo 2 successive additions, and we can see that right here. They said this is the undesired product. So to prevent the second addition, a dialkyl borane is used, and they show us this right here. There would be an example of a dialkyl borane. So the bulkiness of the alkyl groups provides steric hindrance to prevent a second addition. It says the modified borane reagents allow for conversion of a terminal alkyne to the corresponding aldehyde. And for a terminal alkyne, Markovnikov hydration yields a ketone. We can see this ketone right here. Anti-Markovnikov hydration yields an aldehyde. And notice the conditions that they use. That's what you want to pay attention to. Whether you want to make the ketone or aldehyde depends on the reagents used in the steps. So halogenation of alkynes yields a tetrahalide. So 2 equivalents of a halide or halogen are added with excess, halide, and this is either chlorine or bromine. And they experimentally had to determine this. And if you do this, this is carbon tetrachloride. This is the solvent right here. You're going to get a tetrahalide. It says when one equivalent of a halogen is added to an alkyne, both anti and syn addition are observed, and we can see the anti addition, and then we see the syn addition, and that's the minor products. It says the mechanism is not fully understood, so we're not going to be able to show you the mechanism for this. Ozonolysis of an internal alkyne produces 2 carboxylic acids. We see this right here. I'm just going to split it right down there is what happens. It says ozonolysis of a terminal alkyne. So this is terminal right here. This would be an internal up here. Yields a carboxylic acid because you have our carboxylic acid group and carbon dioxide. So we split it right here. We're going to get carbon dioxide and we're going to get the carboxylic acid. So then we can kind of guess, that we're going to get the carboxylic acid here, just cyclopentyl group with our carboxylic acid. We split it right here. Now, if this would have been a hydrogen, we would have got carbon dioxide with it, but it's not, so we get two of these. So ozonolysis of a symmetrical alkynes is particularly useful to prepare carboxylic acids. Only one product is formed, and we get two equivalents of it. We have, here's one, here's two. So that's how you get your two equivalents. It says, recall that terminal alkynes are completely converted to an alkynide ion with sodium amide. We can see this right here. The alkynide ions are good nucleophiles. We get a new carbon-carbon bond. Think for good nucleophile, think SN2, SN1. That nucleophile coming in, and here, this looks like this is an SN2 reaction, and had some type of leaving group, good leaving group. So alkylation of an alkynide ion is an SN2 substitution, and so it works best with methyl and primary halides. If you get something more than that, then the E2 elimination dominates. Acetylene can undergo two successive alkylations. Here's your first one, and then here would be your second one. And sometimes I'll pause on the slide because if you're taking notes, I want to give you the opportunity to be able to take those notes. It says, note that the double alkylation of acetylene must be stepwise. So, there's two steps to it. So in this case, so we're adding alkyl groups. That's what this means by alkylation. And ET is an ethyl group, and ME is a methyl group. So, we could have drawn it like this. They're just abbreviating the shorthand. It says complex target molecules can be made by building a carbon skeleton and converting functional groups. So recall that there's methods of converting triple bonds to double or single bonds. If we want to just take this triple bond to a single bond, all we have to do is use the platinum catalyst. Remember, if we want to just take it to a double bond, we have to poison it somehow. So we use the Lindlar's catalyst, and we can take this to the single bond if we want to. So halogenation of alkene followed by elimination yields an alkyne. So we add those halogen groups to it. Then we have excess sodium amide, and we can get the alkyne. These reactions give us a handle on interconverting single, double, and triple bonds. So we can go from a single bond to a double bond to a triple bond. We can go from a triple bond to a single bond. We can go from a single bond to a triple bond. And that's it. So here's a summary of the reactions, and we're going to get some good practice with this on our homework questions. So what I'm going to do now is I'm going to pause the video. I'm going to get the homework loaded, and we'll come back. So, it might take a few minutes, but we'll be back at it. Okay, I have my homework loaded. I do have yesterday's lecture loaded now, so that should be good to go. So we are in chapter 9. Let me go ahead and open this up. Question 1. So we want to add the appropriate number of hydrogens to this molecule and then give it a name. So we have that. This is 4-methyl. 1, 2, 3, 4, 5, 4-methyl, 2, 15. So we have that one done. There's a second part to it, so this is part 1. Part 2. It's easier just to draw a line, I think. It's 4-methyl, 1-hexyne. So that's question 1 done.
Hi, I don't think you're sharing your screen.
Okay, let me go ahead and share my screen then. I apologize for that. All right, so we should be screen sharing now. So question 1 had 2 parts to it. First part is here, the top. That was 4-methyl 2-pentene, and then the bottom was 4-methyl 1-hexene. So at the 1, 2, 3, 4, 5. 6. All right. We're going to question 2. It says name the alkyne. So this is going to be, 1, 2, 3, 4, 5, 6, 7. This is 4-methyl 2 heptane. I'm going to do question 3 on the same one. It's just another naming. So let's see. So 3 propyl, 1 done. So that 1 through 3 done. We can even do 4 on the same slide too. 4, they give us a name, 3,7-dimethyl 4-9. So we have 9 carbons. Let me see, where do we put? Yeah, so this is it for 4. So we have 3 questions here. All right, so 5 is kind of an interesting question. It says, draw a 6-carbon alkyne that exists as diastereomers. You do not, so we'll draw that. You don't have to draw any wedges for this. Just for an example, if I draw this one, like, I'm not going to draw the hydrogens. This would be, this would be the RS isomer, and then we would have, then this would just be, these two would just be behind like this. Same thing, but instead of solid, we could draw on the dash, then we'd have the SR. So it just flips. So this one makes sense. And you could also have this where it's dashed and this is a solid, which would give you the RR. And then you could flip that around where it's a solid and a dash, and this would be the SS. So that's why that is what it is for. So you want to draw this. All right, so let's go to question 8. Question 8 is pretty easy. I'm not going to draw them all, but they say which one has the highest basicity, which one's the lowest. So this would actually be the most acidic, but we'll just call it lowest basicity, which is the most acidic. You're going to select the one with the triple bond because this has the most S character. This has 50% S, and this one has, what would it be? This would be SP2, so it'd be about 33.33. And this would have the least amount, which would be 25, which would be a single bond. It's based off of S character. All right. So 9 says draw the alkyne form when 2,3-dichloropentane is treated with an excess of strong base such as sodium amide. If we treat it with excess strong base, we're going to get the double bond and then we're going to get the triple bond. So what we're going to have then is this. So that gets, since it's with excess, we're going to go beyond the double bond and we're going to get the triple bond. And on the next problem, problem 10, we show, how to do the elimination. So basically we're going to do 2 eliminations. All right, so let's show you how to do eliminations. That's what question 10 is going to do. Question 10, it says use 3 curved arrows to show the elimination of the first hydrogen bromide. So we'll do that. Remember, we have like sodium amide, so we have this amide coming in. In here. Sorry about that. I have to put a hydrogen there. Let's come in here. I'll take that hydrogen, make ammonia. This will come here, and then this will be released. So that's the first step. Then it wants us to do it again. Now we have a double bond. Still have a hydrogen there. Bromine's an excellent leaving group. We still have, now we have NH3 in solution. We have the bromine. Here's another amide coming in, takes that. Finally, we're left with the triple bond. I'll draw it far apart, that way you don't get confused with it. The bromine. So we have two bromines. We made a couple of ammonia ion, not ions. We made a couple ammonia molecules, and we formed that triple bond. Any questions so far? No, we're moving right along, but nothing was too difficult so far. So next one is pretty easy, to be honest with you. And the reason why I say that is we have platinum. Anytime you see hydrogen and platinum, you're going to reduce that triple bond down to a double bond, followed by another subsequent reduction down to the single bond. So it wants us to show product A. It says we only have 1 mole, so just one equivalent. So we're going to take that triple bond down to a double bond. So anytime you see this, you're going to do a reduction. It doesn't say excess, it just says 1 mole. That's why we're not getting it down to the single bond right away. So here's after 1 mole of H2, and then this would be product A, and then product B, we're just going to take that double bond down to a single bond. So that's all I'm going to do. So we'll show the hydrogens here. So that's what we added. Those questions are really nice. Okay. So let's just say I'm going to put 12 on the same slide. Let's just say, we're going to do the same thing, but we have H2, or sometimes we're going to poison this catalyst, So instead we're going to do, it says use a P2 catalyst. It's a poison catalyst, and we're going to take that triple bond just down to the double bond. That's why they use this catalyst for. So we have this compound. We're going to take that double bond or triple bond 2 down to a double bond. So we will get this right here. now for question 13, it says consider the substrate shown. Let me see that again. Sometimes I have to reload these images myself. I think there was more parts to some of these things, but we're going through it though. Somehow we got mixed up somewhere. I don't know where. I think we're on 11. We did do all the questions though, so we'll just call this 11. It says draw the major product formed from excess hydrogen and palladium carbon catalyst. So, they have carbon, that's some palladium. We'll just have this palladium. You're going to add your hydrogen to this. So we're going to get rid of the triple bond. So wherever that triple bond and double bond is, they're gone. So what we're going to have left is a 6-membered ring. We got rid of this double bond right here. It becomes a single bond. And then we're going to get rid of the triple bond, and it becomes a single bond. We keep the alcohol group. But if we use the Lindlar's catalyst, that's only going to convert the triple bond. So with the Lindlar, we're going to convert the triple bond to a double bond. We're going to leave the double bond alone. We leave this double bond alone. We get rid of the triple bond. Now it's a double bond, and we still keep our alcohol group. Okay, so that's 11. We're going on to the next question. Let me see. Yeah, it says 12, so we'll. So now we're just going to call it the next question. I'll just put a star here. So this will be the next question. So it says draw the product for the following reaction between an alkyne and one equivalent HCl. So we have this. We're adding HCl. So similar to an alkene, a double bond, this is going to come up here. This will be released. And we will have it add by Markovnikov addition. So what we're going to get then is this right here. It's going to be added to the least substituted carbon. And they want a name for it. So let's see. 1, 2, 3. guess this is 12. Yeah. And that was just with one equivalent. If we added two equivalents, that's what the next one wants us to do. We're going to add two equivalents. So what's going to happen is we're going to get rid of the triple bond since it's two equivalents. So this is what the product we're going to form. So we have this. Here is where our triple bond is, but we're going to put the bromine here, and that's where the addition is going to take place. Now, if it would only been one equivalent, we'd have just had one with a double bond, but it's two equivalents, so that's why we have this. And 14, I'll put on the same slide. It says we have, so they give us the keto. Keto means ketone, but now they want us to show the enol. The reason why they have the arrow pointing towards the keto like this, and then a small one going this way, this is more stable. So we have to draw the enol. The enol form is just this right here. So here's your keto, and here's your enol. All right, so that's 13, 14. We go to 15. So 15, it says, okay, we have sulfuric acid and mercury 2 sulfate. And it wants us to add curved arrows. So we may use more than one slide, but that's okay. So we have, I'm going to draw the phenyl ring abbreviated. It just makes it easier for me. So that's a phenyl ring. The triple bond. We do have the sulfate ion in solution. I don't know if they want you to draw that, but it is in solution. So this is step one. So step two would be, we still have that sulfate ion, anion in solution. Now we have the, remember that's your phenyl ring. We have this water. Come here. This will be released. Step 3. That. Step 4 is, so we'll have to put step 5, I think, on another. Well, who knows? Let me see. Let's kind of divide these things up. Put this corner here. Be better if I can put it all on one slide. So with the acid hydrolysis, we get rid of the mercury. That's why I'm going to put this here. It does have an acid hydrolysis step. So we got rid of that mercury. Arrow here with an arrow there. And I think we're going to be able to get it all on. 5. Sorry about that. Ahead of myself. There we go. I have this. That's it. So there's all 5 steps. I'm going to leave that up there for a little bit. So I know you're working on that. All right, so that was 15. Let's go to 16. Does anyone need more time on this question, 15? All right, so 16. Remember, there is homework due tonight, so we do have chapter 8 homework due tonight. So if you haven't done your chapter 8 homework, I highly recommend to do it at some point in time today. As you know, there will be no extensions unless you have a valid excuse. So please, get your chapter 8 homework done tonight. So they give us this on chapter 16. They give us some reactants, and if you go back in the book, you'll see in this chapter, you'll see what we formed. So it wants the initial products. So initially we're going to form, this right here. So I'm going to put the initial right here. And we're going to put the alcohol group on the other carbon for the other one. So that triple bond, we're going to add, one of them is going to go here and the other one's going to go here. So that's what we have to draw next. And then it wants the final products. So we are going to have a mercury catalyst. Let me see. We're going to reduce, we're actually going to take that and we're going to form the ketone product. So this is what we're going to get. So you can think of this as like the enol, and then we're going to take it down to the final products. We have this, and we have this. And we'll do one last one, and I do have an appointment I have to go to today. I will we'll continue on tomorrow. We'll do question 17 though, real quick. 17 says an alkyne of 6 carbons. We have a 6-carbon alkyne. 1, 2, 3, 4, 5, 6. And we just have to put in the triple bond so it can react with either BH3 or with the water mercury. So, and it gives the same product. So to get the same product, we don't care if it's a Markovnikov or anti-Markovnikov. We just have to put the triple bond where we're going to get the same product, and we'll get it right there. So that would be your answer choice. All right, so that's it for today. If you have any questions, please feel free to stay, and I'll try to get those answered and have a great day.